This is what happens when you push a standard, complex text prompt into a high-stakes production environment. Under pressure, the structure shatters. When you pack context, formatting constraints, and instructions into a single block of text, the transformer's attention mechanism loses focus. That drift produces chaotic or misformatted outputs. We call this the single prompt fallacy. Infinitely tweaking a single block of text introduces competing variables, which decreases output reliability the more you refine it. Standard chat interfaces allow for conversational drift. By 2026 production standards, those interfaces are insufficient for systems that require strictly deterministic results. Senior AI architects bypass these flat interfaces by utilizing an internal structural layer, a wireframe of interconnected logic nodes and pathways that operate beneath the prompt. Operating here requires a fundamental mindset shift, treating AI not as a conversational chatbot, but as raw, probabilistic compute. Achieving deterministic results from probabilistic models is a structural engineering problem. To solve that problem, we look at the actual blueprint of a production-grade prompt ecosystem. The goal of this architecture is to force strict compliance, ensuring the model's outputs integrate perfectly with external software APIs. This is the distinction between prompt engineering and AI systems architecture. You are building infrastructure, not just writing instructions. That infrastructure relies on three specific pillars: modularization, recursive logic gates, and semantic triggers. Together, these pillars form a hierarchy beneath the user interface, routing data through rigorous operational protocols. Mastering this architectural scaffolding transforms raw compute into reliable production-grade output. We start by addressing the primary cause of hallucinations: cognitive overload. Asking a model to execute deep logic and complex formatting simultaneously compromises its reasoning. The refactor involves splitting the single prompt into specialized sub-prompts for synthesis, critique, and formatting. The synthesis module acts as the initial data processor. Its only job is to convert raw input into an unrefined draft without the burden of final formatting constraints. That draft moves to the critique module, where internal error-checking nodes scan the logic, isolating flaws without attempting to rewrite the text. Finally, the validated data enters the formatting module, reshaping the content into a rigid JSON structure for deployment. By distributing the load, each module requires fewer tokens to process its specific task, allowing the attention mechanism to focus more precisely. These modules operate invisibly in the backend, abstracted from the user experience. But specialization alone is not enough. We need decision loops to connect these disparate modules safely. Separating these cognitive tasks ensures the model is never forced to handle deep logic and syntax formatting at the exact same time. Linear data pipelines are vulnerable. If the synthesis module fails, a linear system simply passes that error down the chain. To prevent this, we deploy gatekeeper layers, programmatic validation checkpoints situated between subprompts. The gatekeeper validates structural and logical consistency before allowing the data to progress to the next stage. When validation fails, the gate triggers a recursive loop, sending the data back to the previous module for revision. The system automatically injects a self-correcting prompt. The model revises its work based on the error report, and on the second attempt passes the checkpoint. This iterative refinement happens autonomously in milliseconds. These recursive gates force deterministic, repeatable workflows. The model iterates internally until the output meets the required parameters. Recursive logic gates remove the need for perfect first-try outputs, relying instead on programmatic verification. Long-form, multi-turn executions face a specific challenge: continuous context drift. As recursive loops add data to the context window, the original instruction parameters can become diluted. We solve this with state-aware prompting scaffolding. A persistent context block remains fixed while temporary data streams cycle through the system. This persistent scaffolding prevents the transformer's attention mechanism from losing the core constraints during deep reasoning cycles. Within those constraints, we use latent semantic triggers for micro-level control. These are linguistic anchors that prioritize structural integrity over conversational fluidness. This heat map shows how these triggers manipulate the attention mechanism. Attention is strictly concentrated on specific formatting keywords rather than the surrounding text. This precision control guarantees that the final output integrates perfectly with external APIs. State-aware structures and semantic triggers are the mechanisms that bind a probabilistic model to strict mathematical reality. We can now see the entire system operating seamlessly at scale. While currently engineered manually, this architectural framework is being integrated into agentic frameworks. Autonomous compilers are beginning to manage these layered architectures, optimizing logic gates and sub-prompts on the fly. The focus is shifting from manual crafting to the design of systemic ecosystems that evolve with incoming data. Reliability requires stress testing this prompt stack against newly released frontier models to ensure logic gates remain stable. By abandoning the chat interface and mastering this architecture, developers can command AI with production-grade precision.